Our next speaker is Lei Sun from the University of Southampton. He will be talking about runtime deep neural nets, performance scaling through resource management on heterogeneous embedded platforms. And go ahead and take over, Lei. Thank you.
Okay, thanks for the introduction. Hello, everyone. Welcome to my poster. Today, I'm presenting our works on dynamic neural networks and runtime resource management. So first, let me give you some background. Deep neural networks are typically compressed before deployment because they are very computational intensive for embedded platforms. However, the assumed hardware resources at design time might not be available at runtime. A model compression is a trade-off between accuracy and latency, so we don't want to over-compress the model. So in the figure on the left-hand side, model A and E are compressed at the design time to just meet the latency requirement. So in here, we want to compress the model to just meet the target while keeping the accuracy as high as possible. But you can see in the scenario B, C, D, and F, G, H, when the frequency changes at the runtime or when the model is sharing with other applications, the results of design time compression are no longer valid. So one solution to this problem is a dynamic neural network, which is showing on the right-hand side. So in the figure here, we have one dynamic neural network backbone with 4 different subnetwork configurations. For example, the 25% model only use 25% model parameters for inference. And for the 100% model, it is the full model. So the 100% model is generally more accurate, but also slower than smaller subnetworks. At the runtime, we can we can switch between different subnetworks on the fly for different amount of available hardware resources. Here we have some results for the accuracy, latency, and energy consumption trade-off. In the figure, the subnetworks are showing in different color, and the computing element are showing in different symbols, such as the A7 and A15 heterogeneous CPUs on the Audrey X23 platform and the CPU GPU on the Jetson Nano platform. The frequency scaling is showing in different points. So let me give you an example how it works. On the Audrey X23, if we have a 100 millijoule energy consumption target and 400 millisecond execution time target, then the best operating point will be point A, because it has the highest accuracy and it's under the execution time constraint and has the lowest energy consumption. And if we change the constraint to 200 millijoules and 200 milliseconds, then the point B will become the new best operating point. Now, what about power? So here we plot the power consumption trade-off from both platforms on the same figure. And as you can see, the power consumption of a single core CPU scale with the frequency, but does not scale with dynamic neural network. This is because on the CPU, the computational intensity does not change with smaller subnetworks. However, on GPU, we have a different story. You can see that the power consumption scales with frequency as well as dynamic neural network. This is because smaller subnetworks does use less GPU cost for inference. So this is very interesting and very important because we have a new method to reduce the power consumption at the runtime. So in summary, we think that studying the trade-off opportunities in the machine learning model and combining them with traditional frequency and voltage scaling is the key to deliver better performance trade-offs. So in this way, the system can consistently meet the performance target at the runtime when the hardware resources are dynamically changing. And if you want to know more about the dynamic neural networks, please check out our latest CVPR workshop paper. And this is the end of my talk. I'm happy to answer any questions. Thank you.
There is a question. Let's see. I just saw it on chat. And the question is, could it be possible for the different model sizes to share portions of the model parameters? Has that been tried or evaluated? Yeah,
actually, in here, we only deploy one backbone, which is the 100% model. And all the 25% model, 50% model, 75% model are partially are part of this larger model. So they are sharing weight.
Okay, thank you, Lei.
I want to thank our sponsors that made this event possible. So the premier sponsors, Newton, working on automated TinyML. If you were there a few days ago, they had a keynote explaining what they're doing. Executive sponsors are ARM, Edge Impulse as well, and Qualcomm, Sentient, and then our platinum sponsors, we have Infineon and Reality AI. Gold sponsors are Latent AI, SensiML, and our silver sponsors are EMEA, Greenwaves, HOTG, Imagimop, GISO, Seed, and ST. And with that, I thank you very much for staying on till the very last end, the last day of the last session of the last day. And with that, I think we can close the forum for this year. Thank you everybody for contributing. Thank you, Andreas, for also moderating this session.